In this work, we propose a factorized learning framework for temporally grounded video language models. Temporally grounded video language understanding emphasizes event-level perception and localization ability beyond global video-level comprehension. This paradigm is related to diverse real-world applications such as moment retrieval, dense video captioning, and grounded video question answering. We notice that for temporally grounded video language understanding, temporal event level grounding and textual response are two primary tasks that exhibit distinct characteristics yet maintain strong cultural dependencies. Specifically, temporal grounding focuses on precisely locating temporal events that support answering, while textual response emphasizes accurate interpretation from the grounded evidence and generating coherent textual answers. However, existing methods typically handle these two tasks in a coupled manner, with two major limitations. First, various special tokens are designed for temporal grounding, but their generation is mixed with text token generation without a clear logical structure, leading to coupled learning objective and insufficient cultural dependency modeling. More importantly, the special tokens mainly focus on timestamp representation for precise timestamp output, lacking the explicit capture of visual semantics from grounded events. In contrast, we argue that such event-level visual semantics should not be overlooked, as it could inherently serve as informative cultural context for subsequent textual answer generation, especially under the autoregressive paradigm. Based on our analysis, we address it from a factorized learning perspective with three key contributions: a new framework, a new optimization algorithm, and a new supporting data synthesis approach. We first introduce a new framework, D2VRM, that decouples the learning of temporal evidence grounding and textual answering, while also strengthening their inherent cultural dependency. Specifically, we decompose the model response into two sequential stages. First, pure temporal grounding that aims to localize and capture essential visual evidence for response, followed by interleaved text evidence answer generation, where the temporal information is produced in an evidence referencing manner to establish consistency with the previously grounded evidence. Technically, we introduced evidence token, a special token type dedicated to temporal evidence grounding. Different from existing designs of grounding tokens that focus on a special category and timestamp representation, our evidence token emphasizes the capture of event-level visual semantics. Specifically, grounding is first achieved by event-level feature similarity calculation between the evidence token and the frame-level video features. The salient frame-level features will be aggregated in the evidence token to serve as a semantic-rich context for subsequent decoding. To further enhance the model learning on both temporal event grounding and textual response, we introduce a factorized preference optimization algorithm (FPO). Inspired by the existing efficient preference learning algorithm (DPO), we adopt a similar principle, that is, encouraging the model to assign a higher probability of generating a good response than generating a bad response. Here we generalize the standard text-only preference objective into a factorized form with distinct components for temporal event grounding and textual response quality. We found that unlike existing designs, our design evidence token can naturally model such event grounding probability. We directly use the accumulated frame-level feature similarity between evidence token and frame features as event grounding probabilities, and thus integrate explicit probabilistic event grounding modeling into preference objective. To support the proposed FPO, we also construct a synthetic dataset by introducing factorized perturbations into the response sequence. The perturbations are applied at the video event level, considering two main factors: temporal grounding and textual response, along with multiple possible subfactors. The approach ensures a structured and controllable noise generation process, where the cause and types of noise are precisely known without any manual annotations. As a result, our data synthesis process is both reliable and scalable, making it possible to effectively conduct the proposed factorized preference optimization. Our framework achieves state-of-the-art performance across various benchmarks and tasks and a relatively lightweight model size. The ablation studies also verify the effectiveness of the proposed components. More details can be found in our paper. Thanks for watching.